Sometimes you are given the concentration and volume of one aqueous substance. We're going to call that A. So you have this concentration and you have the volume of A. If you have concentration at if you have concentration and volume of A, what can you calculate? If you have concentration and volume, what can you calculate? You can calculate moles. So you're going to use that to find moles of substance A. Could you do that last year? Yeah. Okay. You'll take your liters times your moles per liter and you'll get moles. Yeah, titration is just applied stoichiometry. Okay? You will be asked to find usually the concentration of a second substance, B, that reacted with A. Okay, so what you're going to do is you're going to be like, oh, well, if I found moles of A and the two of them react, I can use my mole ratio to find moles of B. Yes? So the first thing you do you find, that's a 1, doesn't look like a 1, find moles of A. How do you do that? You take your volume and you multiply by the molarity and you find your moles of A. Step 2, you take your moles of A and you use your mole ratio to find moles of B. And at that point, you're just going to stop. Okay, because usually if people try to do the conversion, they usually end up, they end up messing up because you cannot convert your way into a concentration. You have to divide to get a concentration, yes? Because concentration is moles over liters. You can't convert your way into molarity. Okay, so let us take a look at an example here. And this is without knowing the process or anything. You totally do not need to understand the process in order to do this calculation. It requires 15.6 milliliters of 0.200 molar H2SO4 to react with 25 milliliters of NaOH. And they want you to calculate the concentration of NaOH. This doesn't even say anything about a titration, does it? It just says, okay, here we have two chemicals, we are reacting them, and what's the concentration of the second one? So let's just summarize what we know about the H2SO4. H2SO4, we know that we have 15.6 milliliters, which is 0.015 liters. And we also know that we have 0.200 molar, which we can rewrite as 0.200 moles per liter. NaOH. What do we know about the NaOH? We know that it is 25 milliliters, which is 0.025 liters. And we have one other thing that's really important. We have that little word of. So if you don't know what else to do, you can be like 15.6 times 0.2. Yes? It should be 0.015 times 0.2, but sorry, that should be 0.0156. I forgot the 6 there. Times 0.2. So that's what we're going to do. We're going to we're going to find the moles of H2SO4, which is 0.0156 liters of (0.200) moles per liter equals 3.12. Hi. Times 10 to the negative 3 moles of H2SO4. So what we did is, number one, we find the moles of A. And A is whatever you're given enough information to find the moles of. Yes? Step 2, you need to find the moles of B. Who is substance B here? The NaOH. And what do we need in order to go from one substance to another substance? We need the mole ratio. And in order to get the mole ratio, what do we need? We need a balanced equation. So let's write ourselves a balanced equation. I'm actually going to write it up here because I got room. Who are our products? Water. And Na2SO4, yes. Is that balanced? No. Easiest way to balance an acid-base reaction is to say, I need my hydrogens to equal my hydroxides to equal my waters. Yes? So how many hydrogens do I have? 2. So how many hydroxides do I need? 2. How many waters will I get? 2. Done. Okay? So now we have a mole ratio. And then finally, we want the concentration of NaOH, and that's going to be the moles of NaOH divided by the volume of, do I want the volume of the mixture or do I want the volume of the NaOH? Which one do I want to find concentration of NaOH? I want the volume of the NaOH for two reasons. The first reason is that I'm saying what's the concentration of NaOH? So that would be the concentration of the NaOH solution. How much of the NaOH solution do I have? I have 25 milliliters. Also, when these two things have reacted completely, how much NaOH is left? None. So if you do the mixture, your concentration will always be 0 because there's none left at the end. So never the mixture. Never add the volumes. Okay? In a titration, never add the volumes. So that's going to be 6.24 times 10 to the negative 3 moles divided by 0. Sorry, that's titration. Titrn. 0.0250. Yes? Yes. Now, did I steal a lot of questions from other places? Sure. You know, I'm not like reinventing the wheel. On the other hand, even just the organizing of it was a little bit crazy, right? So. And then we need to look at our sig figs. I think we're at 3 sig figs. So that would become then 0.250 molar NaOH. Yes?
Are we going to get questions in which we will get the final volume?
In which you'll get the?
Final volume of the country.
Why would you need that?
I'm
No, because that's not what you're measuring. I mean, if you want to calculate it, you can. But here's how a titration works. You take a pipette and you put, say, 10 milliliters of solution B into a flask. And then you drip from a burette solution A into that flask. You measure your initial volume and your final volume, and you find out how much was delivered. Nowhere are you ever measuring what the final volume is mixed together. Okay? So you measure volume of A, you measure volume of B, you never measure the volume of the mixture. You just don't care because it's irrelevant. The reaction is done at that point. Pardon me? Well, here's the reason we don't add the volumes is because if we add the volumes, we are implying what is the concentration of NaOH after I have mixed them? And the answer is 0, because this is all gone. Yes? So it just makes no sense. Yes?
Is like this part like gonna be on the test because we already did it last
It's going to be on the test.
year.
Yep.
The one from last year, like where you count the steps, so.
Yep.
But it's just the same thing from last year.
Same thing from last year.
And it's important.
And it's important. Okay. But no worries, we're going to do it again in Unit 5 as well.
Oh,
Okay, so
my.
it comes back and back and back.
And then in uni.
And then in uni, if you're taking any chem course, you're going to do a ton of titrations. I would actually love to do a solubility titration with you next week, so if we can cram that in. Yeah. Yeah, finally, right? A lab, I know.
10% of my grade.
Okay. Titration, one lab procedure that allows us to do this whole process, like this is this titration, which allows us to figure out, like, how did we know that it took 15.6 milliliters, right? Because NaOH is a clear, colorless solution. H2SO4 is a clear, colorless solution. Water and Na2SO4 is a clear, colorless solution. How do we know when we have perfectly reacted the two together so they are there in stoichiometric ratio? We need to have an indicator. Yes. Okay. So what we're going to do is we are going to have a standard solution. The word standard means known. And what is known about it? It is a known concentration. We are going to have a sample solution. And the sample solution is the unknown. Usually we put the standard in the burette. Not 100% of the time, but usually the standard goes in the burette. Yeah, the titrant. So the standard solution is also known as the titrant. And the sample solution is also known as the analyte. Why? Because we are analyzing it to find out its concentration. So, the standard, also known as the titrant, known concentration. And this usually goes in the burette. Usually in the burette. The sample solution usually goes in what kind of container? Flask. What kind of flask? Erlenmeyer flask. Okay, now the burette is that long tube with a stopcock at the bottom. That's also known as the tap. Okay, I'm sorry, that's the name. I had nothing to do with it. That's just what it's called. Okay, and this burette shows the volume of a liquid that has been let out. So what you'll do is you'll measure the initial volume, you'll measure the final volume, and then the volume dripped out is the final minus the initial. Okay, so in a burette, the volume dripped out is equal to the final volume minus the initial volume. So it actually starts at 0, right? although you might not have it filled all the way to 0. You might have it filled to like 1 milliliter. If you start at 1 milliliter and you drip out and you get to 9 milliliters, how much did you drip out? If you start at 1 and you finish at 9, 1, 9, how much did you drip out? 8 milliliters. That's how a burette works. Okay? Now like I said, we've got the clear colorless solution. Clear colorless solution. How are we going to know when the reaction is done because we get a clear colorless solution at the end? What we need is an indicator. Okay, and this indicator is a chemical compound that changes color according to the concentration of the chemicals surrounding it. So for example, in the titration we did last year, phenolphthalein turns pink in base. So if you're doing an acid-base titration, phenolphthalein turns pink in base. So what's going to happen is you're going to have your acid in the flask, perhaps, right? Acid in the flask. And you start dripping in some base. And you're making some water. But at this point, you have excess acid, yes? Because you haven't added that much base. And you keep adding acid, and you keep adding base, and you keep adding base until all the acid is used up. At that point, because you're going slowly at this point, you have exactly the right amount of acid to react with exactly the moles of base. Yes? That is what we call our equivalence point. That's where the moles can be converted to moles. Now, the moment you add extra base, you've used up all the acid, the moment you add extra base, now you have a basic solution and the indicator will turn pink. And you'll be like, oh, my reaction is complete. Okay, so the indicator indicates that the reaction is complete. You don't want to go any further than that because now you're past complete. Yes? We usually do not do it that way because looking at the change from colorless to pink is easier to see than from pink to colorless. So usually if we're doing an acid-base titration and we are using phenolphthalein, we will have the acid in the flask regardless of whether it's the known or the unknown. Yeah, you could do it the other way around. Okay? And one of the things you'll do, say in university, is you'll start looking at, what kind of indicator should I select. We'll do a little bit of that this year, but not in huge depth. Okay? All right, so we have our standard, our titrant that does the titrating. The titrant does the titrating. We have the sample, the analyte, which we analyze. We have the burette, which drips the stuff into the Erlenmeyer flask. We have the indicator that changes color when the reaction is complete. The equivalence point is the point at which substance A and substance B have completely reacted and there's no leftover of either. There's no excess. Okay? Hello? Who have we got? That look you gave me, holy mackerel. What is going on?
What is it for?
I don't know. Okay, so this is our equivalence point. It is where substance A and substance B have completely reacted and there is no leftover. And that means that you can use the mole ratio. Now there's 2 E points, which is sad. I'm sorry they both start with E because people find that confusing. There is also the end point. The end point hopefully happens at exactly the same moment as the equivalence point. The end point is when the indicator changes color. Okay, it should happen as long as you've done a good job of choosing your indicator. But, like we'll learn in Unit 5, sometimes you can choose an indicator which changes color before you get to the equivalence point, before the reaction is finished. Sometimes you can choose an indicator that will change color after the reaction is finished. You have to add, like, say, extra base past what you needed to neutralize the acid. And that would be useless. So we're going to do a little stuff in Unit 5 about choosing a good indicator. So the end point is where the indicator changes color. Now, usually when we do this, is it really easy to get the perfect color right away? No. Okay, although you'll find it easier this year. If you did it last year, you'll be better at it this year. You'll be like, oh, I'm not as bad as I don't suck as much as I used to. Excellent. Okay. So would it be good scientific practice to do the titration once and say, this must be perfect. I've got the right number of moles. My volume was correct. Everything is good. What do we do in science if we want to make our data better? We do more trials, okay? Usually in high school, we'll aim for 3 trials, okay? But the more trials you can do, the better. I remember doing an analytical chemistry course, and I usually tried for 5, okay? Now, sometimes you will get an outlier, which is a titration value, like, so you'll calculate your molarity and you'll be like, every time I got really, really close to 1.01 molar, and in this other one I got 1.5 molar. Yeah? Everything else is close to 1.01. And I got one measurement where it's 1.52 molar. Right? And everything else is like, 1.00, and I have 1.09 and, 0.99, and then I got this 1.52 sitting there. That is what we call an outlier. Okay, and it is... Usually we actually just look at the volume to find the outlier, so we just don't worry about it in our calculations. And because you will always be titrating the same volume of solution, you can do that, okay? A titration value that falls outside of the 0.2 milliliter range. So these would all be within 0.2 milliliters. And this one is outside the 0.2 milliliters. And that means it is an outlier, and we omit the outlier from our calculations. Oh, look, omit starts with O. Outlier starts with O. Okay, so here is our procedure. You have your standard solution is usually in the burette. You can see it here. Here's our standard. Our titrant, the known substance, is in the burette. Down here we have our sample solution, the analyte, the unknown. And this little doodad here that lets you drip is the stopcock. And we add also an indicator into the flask. Okay, so the indicator is also in the flask. The indicator will change color when the correct amount of standard solution is added to completely react. At this point, you close the stopcock and then you repeat this process until you have at least 3 volumes within 0.2 milliliters. Any volumes that are not within that limit are called the outliers. And what do you do with an outlier? What do you do with an outlier? Omit from your calculations. Do you guys know the word omit? Okay. I had some grade 9s. They did not know what omit was. So I was like, I don't know. Well, you know, some of them, I don't know. If English is your second language, you might not know it, right? All right, and then you do your stoichiometric calculations. You find moles of A, you find moles of B, and then you find your concentration, and that's it. All right, so here's a little picture of what's happening. We have 10 milliliters of HCl of unknown concentration. So this is our volume of our HCl here, and there's our concentration. And here's our HCl here. Here's our HCl here. This is a 10 milliliter volumetric pipette. Okay, and so you will end up with down here, this is our, no, sorry. We will end up with our 10 milliliters of the HCl of unknown concentration. The other thing we're going to do is we are going to fill our burette. And we know our concentration of our NaOH. The concentration of the NaOH is 0.9973 molar. Okay, so in here we have our sodium hydroxide solution, and we fill the burette, and we find our initial volume. I can't spell. Initial volume, and that is 3.11 milliliters. Okay, we're not measuring it right now. That's 3.11 milliliters. Then what we do is we add some phenolphthalein. Okay, there it is. I've added a few drops of phenolphthalein in there to the flask. And then we drip NaOH until you get a permanent pale pink color. That means that all of the acid is gone and we have excess base. And once we see that pale pink color, then we go over here and we say, what is my final volume? My final volume is 15.82 milliliters. So I started at 3.11 milliliters. I finished at 15.82 milliliters. How would I find the volume of the NaOH? I would take my VF, 15.82 milliliters. This is my NaOH. My VI is 3.11 milliliters. So the volume of the NaOH would be, I would take those and I would subtract them. 15.82 minus 3.11 equals 12.71 milliliters. So we now know the volume of the NaOH. We know that the concentration of the NaOH is 0.9973. Because we're told that in the question. We also know that we had 10 milliliters of the HCl, right? And is this problem any different than the one we did before? The only thing that's going to be different is that the stoichiometry is actually easier because HCl and NaOH react 1 to 1, okay? And that's basically all there is to it. Okay? And so there are some exercises here that let you practice that. Now I do want you to just take a quick look at number 5 on page 81. Because I want you to see what data might look like. This is what data looks like. Okay? So we have our initial volume of the NaOH, we have our final volume of the NaOH, and then we have the NaOH which has been delivered into the flask. And we've done 4 different trials. And we are told the concentration of the NaOH here okay, and when we do the subtraction, we take 16.60 and we subtract 0.32. And we get 16.28, and that's how we find all of the delivered volumes. What do you notice about those values? What do you notice about all of these values compared with one another? Three of these things belong together. 3 of these things are kind of the same. You guys never saw this on Sesame Street, did you? One of these things just doesn't belong here. That's how we play our game. That's how we play our game. And then there was like 3 people bouncing a ball, and there was 1 person jumping rope, and you'd pick out the person who didn't belong. Okay, which one of these things does not belong? That 16.28, yes. These 3 are all within 0.2 milliliters of each other. So, now you know how to do titrations. Okay? So there are questions here about titrations. There's 5 of them. You can work through some of those. I would say at the very least, maybe do number 4 and 5. Okay? Page 80 81, number 4 and 5. Okay, and if you want to do any more, that's fine. You are also going to watch the video for 3.3G and fill it in because that talks about solubility titrations, okay? 3.3G. And just before, we've got 10 minutes left, which is good because I really wanted to do this with you. We're going to talk about what's going to be on the quiz on Wednesday, which is going to be all 5 math types. Okay? And we're not going to go through all of these today, but what I'm going to do is I'm going to do the shortened version of it. Okay? And we're actually going to just grab yourself a piece of paper and we're just going to write down all the types. Okay? Okay, first one, solubility. If I give you the solubility, what can you calculate? You can find the KSP. This type of problem is a dump and stir. And the tools you will use are the solubility equilibrium equation and KSP. KSP, if I give you KSP, what can you find? You can find the solubility. In this one, you will need to write a let statement. You will need to, you'll need to write a let statement. You will use the solubility equilibrium equation and you will use KSP. This is also dump and stir. I didn't put it in there, dump and stir. So the first 2 types, dump and stir, dump and stir, dump and stir. 3, will a precipitate form? This is mix and match. You will use dilution calculations. You will use the solubility equilibrium equation and Q. So will a precipitate form is a mix and match. Minimum and maximum problems. Those are the ones we did yesterday. What's the minimum without a precipitate forming? What's the maximum without a precipitate forming? What's the minimum to get a precipitate to form? This is also mix and match. And for this one, you'll need to use the solubility equilibrium equation and KSP. And finally, what did we do today? Titrations. You will use the precipitation equation. And then you'll use moles and stoichiometry. Okay, so that last one is very different. So you've got 2 dump and stir, 2 mix and match, and 1 stoichiometry. Yeah? Okay. Now, in order that you don't forget about any of those types of problems over the weekend, I'm going to give you like 1 or 2 from each. Okay? So you've got 1 or 2 titrations. We got, let's see what we got here. We need page. Okay, let's do page 59. Now, all of these, you can be like, oh, I don't remember how to do this one on page 59. You can go back to the pages before that and all the examples will be relevant. Yes? No, 59 is not titrations. This is titrations. Okay? 59, you're going to do 5 and 6. Oh yeah.
It's gonna be posted on Teams, right?
Yes. 66. Number 4 and 5. So there's a lot of math this weekend, okay? Number 3 and 4. And page 75, number 2 and 3. Okay, so that's 2, 4, 6, 8, 10 math problems. So spread them out, don't try and do them all at once. Or maybe you're like, I don't have time for 10 math problems, do 1 of those 2. Do you know what I mean? And then if you have extra time, work on the review. So yeah, big chemistry weekend this weekend. I'm sorry.
Miss Princess, I have a question.
Yes.
Like for the rice table, do we
Yes.
use the ratio of moles or ratio of the molarity? Which one?
In a rice table, because it's you use molarity,
Oh,
but molarity will be proportional to moles,
Oh,
right? Because it's
yeah.
moles per liter, right?
Then what about in titration equation?
In a titration,
yeah, like for
you
the
can
equation.
use a RICF because
Oh,
it goes
I
to
see, I see.
completion. It
Yeah,
doesn't
yeah,
form
yeah.
an equilibrium.
But in that situation, do we use moles or we use molarity?
Moles.
Oh, I see,
Moles.
I see.
Yeah.
So the original one is moles, then molarity. Wait, molarity? Then
So if you want to use
yeah,
a rice-like table,
Yeah.
I'm going to call it a RICFA table.
yeah.
Right? If you want to use a RICFA table,
Yeah.
you can use moles in that. But if you're doing an equilibrium, an RICE for equilibrium,
We use
that's going to be molarity.
molarity.
Yes.
Okay.
Okay. Yeah.